In this video, we're going to be taking a look at part 2, 3, and 4 of trig integrals. So these are integrals where we have a trig function in the integrand. Part 2 will be looking at powers of tangent by itself. And then part 3, I believe we look at powers of secant by themselves. And then in part 4, we mix tangents and secants together. We'll find that the mixing of the tangents and secants is going to bring up some strategies very similar to what we saw in the last video, where we used Pythagorean identities to reduce the integrand to something we could integrate directly or that we could use U substitution on. So let's go ahead and get started. We're going to take a look first at part 2, trig integrals, integer powers of tangent. Let me share my screen with you so that you can see what I'm looking at far more simply. Now, when you're looking at it, you're looking directly at my notes here, and you'll see that on the left side, I have the navigation menu open. And you'll see that there are, again, multiple parts and multiple cases. And within the cases, sometimes there are types. So yes, it's complicated. Trig integrals are difficult. There are so many different possibilities for how to integrate these. But we're going to start with powers of tangent. So integrating powers of cotangent is similar. You just replace tangent with cotangent, secant with cosecant. So basically, we'll be covering both when we talk about tangent. We'll start with the very simplest one, and that's simply that the power on tangent is a positive 1. Now, this should be something that you already know how to do. You should have done this in Calculus 1. So what am I talking about? I'm talking about the integral of tangent of x dx, which we can rewrite as the integral of sine of x divided by cosine of x with the differential dx. Now, you should already know how to do this one, but in case you've forgotten, this is a basic U substitution. U becomes the denominator, which is cosine of x, and du is negative sine x dx. And then you have 1 over u with a negative du, and that gives you the natural log of the absolute value. So yes, you can go ahead and integrate this one directly. So tangent to the first power of x, we can already do coming out of Calculus 1. It's just a U substitution, 1 over u du. Now let's suppose that the power on tangent is a negative integer of some kind. Well, then you just rewrite it in terms of cotangent, which is the reciprocal of tangent. So now the power is positive, it's not negative. And then we'll move on to part 2, case 3 below, with cotangent as the trig function instead of tangent. So dealing with a negative power of tangent is really just integrating cotangent with a positive power. Now let's take a look at something that's more difficult. And this would be, of course, case 3. The power on tangent is some integer greater than 1. Now, we're not going to deal with fractional powers or roots, heaven forbid. Those probably don't even have an antiderivative. We're looking at the case where you have tangent to some power of x dx. Now, it doesn't have to be x. It could be 2x, 6x. Then you got to be careful with the chain rule when you're looking for du on a U substitution. M is something greater than 1. In other words, it's some power greater than 1 on tangent. This strategy is very similar to what we've done before, except this time, instead of just pulling 1 off, as we did in the sine and cosine, we're actually going to pull 2 of the tangents off. Now, your options are that you have 2, 3, 4, 5, something like that as the power on tangent. If you only have 2, that's okay. You're just starting with the integral of tangent squared of x dx. But if you had 3, 4, 5, 6, 7, something like that as the power on tangent, you're going to pull 2 of the tangents to the side, and then you're going to have what's left. So let's say you had tangent to the 5th. Then you're going to make that tangent to the 3rd times tangent squared. So you're going to pull 2 off instead of 1. So with sine and cosine, we pull 1 off to become part of du. And with tangent, we pull 2 tangents off. Now we're going to use a trig identity, which of course is that second trig identity that we saw in the first video on trig integrals. And that's tangent squared equals secant squared minus 1. Now this is going to replace the two tangents that we pulled off, where we pulled off tangent squared. So we're going to replace that with secant squared minus 1. Now, do you see where this is going? I hope you do. So what we're going to have then is, keep in mind that the derivative of tangent is secant squared. So we're going to be able to borrow this secant squared to be part of du. Now that second one with the minus 1, that's going to cause us a little bit of an issue. So let's see what we've got now. So after you've multiplied this out, what you started with was tangent to some power, and then you pulled off 2 of them. So you had tangent to the m minus 2 times tangent squared. And then you replaced the tangent squared with secant squared minus 1. So let's write that over here to the side. You started with tangent to the m of x dx. And then you wrote that as tangent. You pulled 2 of the powers off. And then you had this as tangent squared of x dx. And then you left the first factor alone, tangent to the m minus 2 power of x dx. And you replace the second one with secant squared of x minus 1 dx. And then you do the distributive property. So you have tangent of m minus 2 of x dx times secant squared of x dx minus the integral of tangent of m minus 2 of x dx times dx. Now this gives us 2 integrals. We can call them I1 and I2. I1 is ready to go. We have a u substitution that's just begging to be done. We would let u be tangent of x, and du would be secant squared of x dx. So this first one, I1, is ready to be integrated with this u substitution you see in the middle. What about the second integral? It's not. We're basically back to where we started, right? So if I had started with tangent to the 5th or something like that, this would now be tangent cubed of x secant squared of x minus tangent cubed of x dx. Well, how do you deal with tangent to a power greater than 1? Pull 2 of the tangents off, convert it. In other words, you have to start the process again. So this second integral, you have to apply the technique another time, at least, in order to get it down to something you can integrate. Let's take a look now at example 6, which is tangent to the 4th of x dx. We want to take a look at how this one integrates. So remember, with tangent, we're going to pull off 2 powers. So this is going to be rewritten as the integral of tangent squared of x dx. Oops, I'll leave the dx to the end, times tangent squared of x with a differential at the end. Now what do we want to do? Well, I've got 2 tangent squared, so I'm going to take the second one and I'm going to convert it using the Pythagorean identity. So this first one remains tangent squared of x, and the second one becomes secant squared of x minus 1 dx. Okay, then we distribute, right? So we're going to distribute this out. So we have the integral of tangent squared of x times secant squared of x dx minus the integral of tangent squared of x dx. Now the first one is ready to integrate using a u substitution. So let's go ahead and focus on the first one, and then we'll come back and we'll focus on the second one to finish it out. So this tells me I've got u equal to tangent of x, and du is secant squared of x dx, which I have in the integrand. So this just becomes the integral of u squared du. So this becomes the integral of u squared du, which becomes 1/3 u cubed plus a constant, which I can then rewrite as 1/3 tangent cubed of x plus my constant. Now I'm going to get a constant from the other one and I'll roll them together. All right, a constant plus a constant is still a constant. Okay, so this takes care of the first one. What about the second one? Well, remember, if you have tangent raised to a power greater than 1, we pull off 2 and we convert it. Well, I only have 2. Well, then those are the 2 that I need to convert. So in the second one, I'm going to go ahead and I'm going to convert. So I'm going to rewrite this one as minus the integral of secant squared of x minus 1 dx. then I can distribute the negative and split it into two integrals, minus the integral of secant squared of x dx plus the integral of 1 dx. These both integrate directly. They have antiderivatives. The antiderivative of secant squared, of course, is tangent. And so this is just going to give me minus tangent of x plus its constant plus x plus its constant. Now let's roll all of these constants together, and then we come up with our final solution. Oops, my 2 turned into a 3 somehow. I didn't quite finish drawing it, did I? So this becomes 1/3 tangent cubed of x minus tangent of x plus the constant that gets rolled in from all of them, right? And that's how we integrate a power of tangent that's greater than 1. Okay, we've dealt with powers of tangent. Let's now take a look coming down here at part 3, integrating powers of secant. This would be similar if it were cosecant. We would just replace secant with cosecant and tangent with cotangent. Now there's multiple cases of this one as well. So we'll start basically the same as we did on powers of tangent. What if the power on secant is 1? In other words, I'm asking you to integrate secant of x dx. Now, some of you memorized this in Calculus 1. I'm not a big fan of memorization because I find that memorization tends to disappear over time. If you understand the strategy, though, you can always rederive the answer. That will stick with you for years. The strategy here is a technique or a trick, which is to multiply by a form of 1. So secant of x plus tangent of x divided by itself is equal to the number 1. So we're going to multiply this by this particular value that you see here. So we're multiplying by secant of x plus tangent of x over secant of x plus tangent of x. That's just the number 1 in disguise. Now, because it's secant times this fraction, I multiply the numerators together, and the denominators are just 1 and the secant of x plus tangent of x. So this is going to change my integrals look to become secant squared of x plus secant x tangent x divided by the denominator secant x plus tangent of x with the differential still of dx. Now we can do a u substitution similar to the one we did for tangent, where we allow u to be the denominator, which is secant of x plus tangent of x. Now, why would we do that? Because the derivative of the denominator is in the numerator. The derivative of secant is secant tangent, and the derivative of tangent is secant squared. So we essentially have the integral of 1 over u du, which becomes the natural log of the absolute value of u. So this becomes the integral of 1 over u du, where u is that denominator, secant of x plus tangent of x. So this is a trick. You can use the same trick to integrate the integral of cosecant of x dx. Instead of using secant plus tangent, you would use cosecant plus cotangent divided by cosecant plus cotangent. So you change all the trig functions to their cofunctions. And this, of course, gives you the natural log of the absolute value of u plus a constant. Don't forget the absolute values. They're part of the antiderivative. So that's how we would deal with secant to the first power. What if we have secant to the second power? Well, then you shouldn't even be asking me how to integrate that. It has an antiderivative. The antiderivative is tangent of x. So you're done. But really, I should have a plus c here. So don't know where that plus c drifted off to in the notes, but there should definitely be a plus c there since it's an indefinite integral. So we've dealt with secant to the first, we've dealt with secant to the second. What if we have a power on secant which is greater than 2? Well, then we have two possibilities. It's an even integer or it's an odd integer. And I hate to tell you this, but they're different. All right, now similar in that we use similar techniques, but different in that we need a different technique slightly. So we're going to start in case 3, where secant's being raised to a power bigger than 2, but it's an even integer. So if it's bigger than 2 and even, It's got to be 4, 6, 8, 10, 12, and so on. So at a minimum, power of 4, and then even. So what is our strategy? Just like with tangent, where we pulled off 2 of the tangents, we're going to pull 2 of the secants out here. So very similar idea. So that will give us secant to the m minus 2 times secant squared of x dx. So we pulled 2 off. And then we've got m minus 2 of them here. Now remember, m started out even. And if you take an even number and you subtract 2, it's still even, right? Which means I have an even number right here on this secant to the m minus 2, which means I can write them in pairs. Do you see where I'm going with this? If I can write those in pairs, then I can use the trig identity that secant squared is tangent squared plus 1 to replace all the secant to the m minus 2 pairs with powers of tangent squared of x plus 1. All right? Now that leaves secant squared sitting over here to the side, and it becomes part of our du, where our u becomes tangent. So we've reduced this into something where we can now use u substitution. Our u becomes tangent of x, and our du is secant squared of x dx. So this becomes u squared plus 1 to some even power secant squared of x dx, which is du. All right? Now, that one is very similar to what we saw before. Let's now look at case 4. Case 4 is a little bit different. In case 4, we have secant raised to a power bigger than 2, but the power is odd. It's not even. This is going to be a little bit different. So if it's an odd integer, then it's got to be 3, 5, 7, 9, etc., at a minimum of 3. These are somewhat unpleasant. I'm sorry, but this is where integration by parts rears its ugly little head, all right? So we're going to need some integration by parts to integrate these. So we have secant being raised to an odd power. So let's suppose over here to the side, we'll say that we had secant to the 5th power of x dx. Well, the strategy is the same. We're going to pull 2 off. So I have secant to the 3rd of x times secant squared of x dx, all right? So I'm pulling 2 off. Note that because I started with an odd power, when I pull 2 off, what's left is still odd, all right? So it maintains that quality, all right, of being odd. Now we're going to use integration by parts. Now these are not pleasant. How are we going to do integration by parts? Well, when we look at the integral here, we can see that we have got multiplication in the integrand. Now, this is one of the ones that I did not cover when I talked about integration by parts. What we actually have here is we've got the same trig function being multiplied by itself with a different power, and yet I'm going to do integration by parts. This is unusual for integration by parts. It's actually a technique coming out of the trig integral. So this is an unusual time to do integration by parts. What we're going to do is we're going to split, and we're going to allow dv to be secant squared of x, and with the dx differential, and u will be what's left of when I pulled off the 2. So that would be secant cubed of x dx right here. So my u would be secant cubed of x, and I'd take the derivative of it. 3 times secant squared of x times derivative of secant, which is secant tangent, which would give me a boatload of secants. And then dv would be secant squared of x dx, which I have to integrate. So remember the formula for integration by parts, uv minus the integral of v du. So the integral of u dv is uv minus the integral of v du. Let's go ahead and write that down so that we don't forget what we're doing. U times dv is equal to u times v minus the integral of v du, right? So we're going to do integration by parts. We're going to start with a more simple one than secant to the 5th. We will probably look at secant to the 5th, but we're going to start with the simplest of these types, which is secant to the 3rd of x dx. It's an odd power bigger than 2, the smallest odd power bigger than 2, secant to the 3rd. So what are we going to do in order to integrate this one? In order to integrate this one, what we need to do is to pull off, and I'm trying to figure out where I am in my notes. Hang on, right? I must have moved my notes around a little bit. I'll find it. So I'm going to pull off 2, all right? So that was the strategy. Pull out 2 secants and leave the others. Now let's see what that gives. Coming down here, we're going to rewrite this then as the integral of secant of x, which left when I pull off 2, times secant squared of x dx. Now I'm going to do integration by parts. So my integration by parts, my u is equal to secant of x. That's this first part right here. This is my u. And the second part over here, this is dv. So dv becomes secant squared of x dx. Now remember what the pattern is for integration by parts. You take the derivative of the u side and you integrate the dv side. So the derivative of u, abusing the notation to swing the dx around, gives me secant x tangent of x dx. Now when I integrate secant squared on the 2 sides, I get v is equal to tangent of x. Now, remember that normally that would give me a plus c, but we're choosing the specific antiderivative where c is 0. So we're choosing a specific one. And then our pattern is upper left times lower right minus the integral of the product of the bottom row. So that's the pattern for integration by parts. So coming over here, the integral of secant cubed of x dx is equal to secant x times tangent of x, that's u times v, minus the integral of v, tangent of x, times du, secant of x, tangent of x, dx. All right? So now when I look at this one, we're going to have a slightly different one. So I've got secant of x, tangent of x, minus the integral of tangent squared of x times secant of x dx. Now, we haven't talked about how to mix the 2 together yet. We haven't done that yet. So let's think about what strategies we might use when we're mixing tangent and secant together. What strategies did we use previously? I mean, what do you think might work here? I've only got a single secant of x, but secant of x is not the derivative of anything, right? The derivative of secant is secant tangent. And the derivative of tangent is secant squared. So this is going to have a hard time being part of du for anything. Well, that only leaves me with the tangent squared of x. And of course, we'll go into more detail with these when we get into part 4. But basically, all I'm left to struggle on with is this tangent squared. Well, what could I do to that tangent squared? Well, I don't really have any other options. The only thing I have, the only technique in my toolbox is to convert this using the Pythagorean identity. So that's what we're going to do. So now what we're going to do is we're going to take this, the secant of x, tangent of x is going to follow along. And then we're going to replace the tangent squared of x with secant squared of x minus 1 multiplied by secant of x dx. You may say, well, gosh, that doesn't look a whole lot better. That's going to give me powers of secant. Yes, it is. All right, let's see what powers of secant we get. So continuing down another line, this is going to give me secant x tangent of x from uv minus secant squared times secant is going to give me secant cubed. So I have minus secant cubed of x dx. And then a double negative will make it a plus, the integral of secant of x dx. Now, you may be panicking at this point and going, but that's worse, right? Except it's really not. I know how to integrate secant of x. We talked about that. That's the technique where you multiply by secant plus tangent divided by itself, and you get 1 over u du, which is the natural log of the absolute value of secant of x plus tangent of x. This one we can integrate directly, so we know that one's done. This one is the one that's probably causing you some anxiety. But notice that this is a multiple of what's on the left side. In fact, these are like terms. They're like integrals. They're both integrals of secant cubed of x dx. So what I'm going to do is I'm going to take this negative secant cubed of x dx, and I'm going to add that to both sides of the equation. So you may be asking yourself, am I allowed to do that? And the answer is yes, you are allowed to do that. They're like integrals. They are like terms. So this is going to add over here. And as you might expect, when you add secant cubed of x dx, the integral to itself, you get two of those integrals. So now let's go ahead and go down one line. I'm not going to work out the integral here since I've already done it for you once today. I'm just going to write down the result that we had previously. So now we have two integrals of secant cubed of x dx, which is equal to secant of x tangent of x plus the natural log of the absolute value of secant x plus tangent of x. That comes from the integral of secant of x. And don't forget, we've got a plus c running around over here because we have the integration, indefinite integral. Now, how can I solve for secant cubed of x dx? Well, you just divide by 2. So I'm going to divide every term by 2. A constant divided by 2 is still a constant. And so I end up with the integral of secant cubed of x dx equal to 1/2 secant x tangent of x plus 1/2 the natural log of the absolute value of secant of x plus tangent of x. That was the technique we looked at first, plus a revised constant, right? And that's the result. We're essentially done. So now you know how to break down these powers where the power is odd. You're still going to pull off 2, but you're going to have to do integration by parts. Let's make it a little bit harder now, and let's look at a more difficult one, which is secant to the 5th of x dx. So the power on secant is higher. It's not 3, which is the lowest possible greater than 2. This is now 5. It becomes much more difficult. And as you'll see, it's going to actually involve the integral that we just did. So now let's go ahead and break this one down. So we're going to rewrite this by pulling off 2. So that leaves us 3 for the first part. And then we have the secant squared of x dx over here for the next part. Now we want to do integration by parts. I know it's tempting to want to integrate them separately by breaking apart that product, but that's not allowed. You cannot break integrals across multiplication. So what we have to do is we have to come up with a u and a dv. So this part right here becomes our dv again, and this part right here becomes our u. So remember that we have the integral of u dv is equal to uv minus the integral of v du. So our u is equal to secant cubed of x, and our dv is equal to secant squared of x dx. So we're going to integrate the right side the same as we did before. And this tells us that v is equal to tangent of x. And we're going to choose the particular antiderivative to be the one where the constant is 0, because we know we're going to have constants at the end. And then we have to take the derivative of the u side. So when we take the derivative of the u side, then we have to invoke the chain rule. So the power is 3, so power comes to the front, reduce the power by 1, and that gives you 3 secant squared of x. And then we have to multiply by the derivative of the inside function, which is secant. So that gives us secant x tangent of x. And then we abuse the notation and swing the differential dx around to the right. So I actually, if I want to simplify du a little bit, I could rewrite du as 3 secant cubed of x tangent of x dx. Now my formula for the integral of secant to the 5th of x dx is going to be u times v. So I get secant cubed of x tangent of x minus the integral of v du tangent of x times 3 secant cubed of x tangent of x dx. Now you may look at that and go, oh, that looks awful. Yeah, it does. I didn't say these would be fun. These are complicated. They're hard, all right? Trig integration is not a simple thing. So the first thing we want to do here is probably clean it up a little bit and rewrite it in terms of what the new one is going to be. So now what we're looking at here is we've got secant cubed of x, tangent of x, minus 3, the integral of tangent squared of x, times secant cubed of x dx. All right. Now this is actually part 3, case 3. So we're kind of doing them all together at the same time, just to save a little bit of time in the video. So they're all kind of getting mixed together. So in other words, I really can't figure out how to do powers of secant by itself without knowing how to do powers of tangent and secant together. So probably I should have started with that, but that's okay. We're already most of the way through this one. So what would be our next strategy? I mean, what would you do here? I mean, what would you convert? Well, I've got secant to the cubed of x. I could pull off 2 and convert to tangent, and then I'd have 1 secant by itself. But secant by itself is not the derivative of anything. So it can't be a du. So that's a bad option. So I don't want to do anything with this. Well, what about the tangent squared? I've got 2 of those. So I've got a pair. So I could use the Pythagorean identity to convert that one. Let's try it and see what happens. Sometimes you just have to take a leap of faith and try something. So this part is coming straight down. So we have secant cubed of x, tangent of x. That's not going to change. Hopefully I copy it correctly each time. And then we have minus 3, the integral, and then we're going to replace tangent squared with secant squared of x minus 1. Again, using the Pythagorean identity substitution. And that will give us something that only has secant in it. And you may go, oh God, but those are hard. Yeah, they are. But you're going to find out that one of them is again going to be a multiple of the left side. It's going to be a multiple of secant to the 5th. And the other one is going to be secant to the 3rd, which we've already integrated just a minute ago in the previous example. So let's go ahead and multiply this out. So I have secant to the 3rd of x, tangent of x, minus 3, the integral of secant to the 5th of x dx. Remember, doing the distributive property. So 3 times secant of x times secant cubed gives me a negative 3 secant to the 5th of x. Then a negative 3 times a negative 1 is 3 times secant cubed of x dx. So plus 3, the integral of secant cubed of x dx. In other words, in order to integrate the 5th power of secant, I have to be able to integrate the 3rd power of secant. Not so much fun. But we've already done it, so we can borrow the solution from previous, and we'll be able to substitute that in. Now let's look at what we've got. I know that I've already worked this one out, so I can substitute that answer in. This is a negative 3 secant to the 5th of x dx, which is a multiple of what I'm trying to find. So I'm going to add this one to both sides of the equation to get my 2 like integrals together. So the next thing I'm going to do is add the 3 integral of secant to the 5th of x dx to both sides of the equation. Now let's see what we get coming down for the next. I had 1 up here and 3 there, so that gives me 4 integrals of secant to the 5th of x dx equal to secant cubed of x, tangent of x. I don't want to change too much at one time, plus 3, the integral of secant cubed of x dx. Now we've already worked that one out, so let's go ahead and remember what we got for that one, and we'll substitute it in. So this was from example 7, which the integral of secant cubed turned out to be 1/2 secant tangent plus 1/2 natural log of secant plus tangent plus a constant. So let's go ahead and put that in there, and then we'll be close to being done, but not quite done yet. So this is going to give us secant cubed of x, tangent of x, our original u times v plus 3 times, this is 1/2 secant x tangent x, plus 1/2 natural log the absolute value of secant x plus tangent of x. And then, of course, all of this is going to get a plus c on the end because it was an indefinite integral. So it's only good up to a constant. And then I've got to multiply through by the 3. Okay, so that would give me 3/2 here and 3/2 here. Looks good so far. But I'm not looking for 4 times the integral of secant to the 5th. I'm looking for the integral of secant to the 5th, so I need to divide by 4. So my 3/2, when I divide by 4, is going to become 3/8. So my final answer, if I can find it down here, becomes 1/4 secant cubed of x, tangent of x, plus 3/8 times secant x, tangent of x, plus the natural log of absolute value secant plus tangent with a constant at the end for the indefinite integral. So you can see that this is a pretty long process and definitely not an easy one to do. And in order to integrate powers of secant, we actually had to know how to integrate products of secant and tangent. But again, the strategy was basically the same in that there wasn't an obvious, there was an obvious choice because secant by itself is not the derivative of anything. So we had to convert the other one using the Pythagorean identity, and that's going to be our strategy. Okay, we have completed that part. So now we're ready to look at part 4, which is officially products of tangent and secant, which we've pretty much already dealt with, but we'll go through it just to make sure that you're up on all possible different variations of these. So products of cotangent and cosecant would be similar. You just replace tangent with cotangent, secant with cosecant. Be careful with the derivatives, they'll have negatives involved. So when we're looking at this, we have tangent to some power times secant to some power. But again, note that the arguments to the trig functions match. They have to match. We're not going to be dealing here with ones where the arguments don't match. We could, but it just gets, it's enough already, right? In fact, it's already too much. So enough is enough. We're not going to deal with that with tangent and secant. So we're going to start with n being a positive even integer and m being any constant. So we've already seen this in one of the examples we did up above. This is going to be similar to case 1 for sine and cosine. So basically what we have here, if n is 2, then we've got secant squared of x dx, which secant squared is the derivative of tangent. So it's just like begging you, please do a u substitution, let u be tangent and let the derivative be secant squared. Well, what if you had 4 of them? All right, 4 is a positive even integer. Well, then you would split them. So again, you're going to pull off 2 secants. Remember with sine and cosine, we pull off 1, and with tangent and secant, we pull off 2. So we're going to pull off 2 if we have 4. 2 of them are going to stay secant squared to serve as the derivative of tangent. The other 2 have to get converted using the Pythagorean identity into some expression involving tangent. So let's take an example down here. All right, so we started with tangent to any power, and the power on secant was even, and let's say it was 4. So we pulled off 2, and that leaves 2 here. These 2 are going to stay secant squared to be the derivative of tangent. This secant squared is going to get converted into tangent squared plus 1, which is the Pythagorean identity involving these. So tangent squared plus 1 replaces these guys in the middle, each pair of them. Don't convert this last one because then you lose your du. All right? Then you use u substitution, letting u be tangent of x and du being secant squared of x. So let's take a look at an example of one of these. This is tangent cubed of x, secant to the 4th of x dx. Okay, so let me see if I can find this one in my notes somewhere in here. Tangent cubed times secant to the 4th. There it is. All right. So what do we want to do? we want to, since we have an even number of secants, and we know secant squared is the derivative of tangent, then we're going to split the secants. So this is going to be tangent cubed of x, secant squared of x, secant squared of x, and the differential is dx. Now, the next thing that we want to do is we want to leave the secant squared of x dx alone. This is going to be our du. So we're going to leave this guy alone to be du. And we need to convert this guy. All right, so this is going to give me the integral of tangent cubed of x. Secant squared becomes tangent squared of x plus 1. And then I leave alone my derivative, secant squared of x dx. Now I'm going to do a u substitution. So my u is going to be tangent of x, and my du is secant squared of x dx. So this one is not too terribly awful. It's actually kind of easy compared to what we saw with powers of secant. So u is tangent of x, and du is secant squared of x dx. So this can be rewritten then. We have the integral of u cubed times u squared plus 1 times du. Well, that just becomes a polynomial integrand, so we can use the distributive property to multiply that out. Remember, when the bases are the same, you add the powers, don't give me 6. So u to the 5th plus u to the 3rd with du, and this is going to integrate very simply. 1/6 u to the 6th plus 1/4 u to the 4th plus a constant of integration, which is 1/6 tangent to the 6th of x plus 1/4 tangent to the 4th of x plus a constant. So this is more similar to what we saw in the first video when we were looking at products of sine and cosine. It's a more straightforward, more simple way of doing it. We've already done the really awful ones, which are secant to a power, okay? All right, let's take a look at case 2 now. So that was case 1, where the power on secant was even, and that enabled us to pull off 2 and have an even number left. Now we want to look at the next thing, which is that the power on secant is not even. All right, if it's not even, then there are 2 options. The power on tangent is odd, or the power on tangent is even. But at any rate, the power on secant is definitely odd. So we have secant to an odd power. Now, unfortunately, there are 2 cases here, so we can't do tangent to any power like we did last time. We had secant being even, don't care about the power on tangent. This time, we have to split it into 2 subcases. Secants raised to an odd power, tangents raised to an odd power, so both odd. This is going to be a little difficult. So what are we going to do here? I mean, if I pull off 2, which is what I would normally do, it would leave 1 of each. It would leave 1 tangent and 1 secant. But if I have 1 tangent and 1 secant, I have secant times tangent, and that is the derivative of something, is it not? Yes, as a matter of fact, it is. Secant times tangent is the derivative of secant. So that's going to be our strategy. So we'll go through some of the subcases here, the subtypes here. If both m and n are 1, then you really shouldn't be asking me. This is just the integral of secant tangent, which is secant of x plus the constant of integration. So that's what I'm talking about. Secant times tangent is the derivative of secant, right? So the antiderivative is secant. Then what about if the tangent has a power of 1 and the power on secant is odd and bigger than 1? So 3, 5, 7, 9, something like that. Well, we're going to pull one of the secants off, and then we'll have secant tangent, and then we'll do a u substitution with u being secant of x and du being secant tangent. So let me write just a real simple example of what this would look like. So let's say you had tangent of x, secant to the 7th of x dx. Notice the arguments match. Then what we would do is we would rewrite this as secant to the 6th of x, and then the secant x that we pulled off and the tangent of x with the differential dx, this becomes du, and we let u be secant of x, right? So it becomes u to the 6th du, which we can integrate pretty easily. All right, so that one's not too bad. What if m is odd bigger than 1 and n is 1? Well, then it's essentially the same thing, but with the roles reversed. I'm going to do the same thing. I'm going to pull 1 off the tangent, and then I'll have secant tangent, and then I'm going to have to do something a little different because I'll have powers of tangent, even number of them. Since m started odd, when I pull 1 off, it'll be even. All right, so if I have something like that, let me go ahead and write down an example so that you can see what it would look like. Let's suppose that we had tangent cubed of x, secant of x dx. So I'm going to pull one of the tangents off. So I have tangent squared of x, secant x, tangent of x. Now I want to use the secant of x, tangent of x dx as du, but it's the derivative of secant, not tangent. And I've got tangent squared, so that's got to go. So what do? Well, I do a Pythagorean identity substitution, and I replace the tangent squared with secant squared minus 1. So this would become secant squared minus 1 times secant x tangent of x dx, which would split into 2 integrals. Secant squared of x, lost my x there, times secant x tangent x dx, minus the integral of secant x tangent of x, which integrates, right? That's just secant of x. And the first one becomes a u substitution where u is secant of x and this is du. So again, it will go ahead and integrate pretty easily. But notice that what we're doing is we're pulling off and we're rewriting it in such a way that we have an even number of the others. And this time we're forming the differential here of secant tangent rather than secant squared, right? Now let's take a look at example 10, which is tangent to the cubed of x, secant of x dx. We want to take a look at how we integrate this one. All right, so when we're looking at this one, we have tangent cubed times secant. Now we know secant is not the derivative of tangent, so we've got to get something in there in order to be able to integrate it. And what are we going to use? Well, what we're going to use then is going to be pulling off one of the tangents so we can form secant tangent, and then we'll have tangent squared. So this is going to become tangent squared of x, secant x, tangent of x dx. Now we want to use this as our du, which means our u will have to be secant. But I don't have secant, I have tangent squared, so I'm going to replace it as I showed you up above. So this is going to become the integral of secant squared of x minus 1 times secant x tangent of x dx. Distribute it out and split it into 2 integrals. Secant squared of x times secant x tangent of x dx minus the integral of secant of x tangent of x dx. Now the second integral will integrate directly because this has an antiderivative, which is secant of x. So I know that this one goes immediately and becomes secant of x plus my constant. Now what about the first one? On the first one, I want to do a u substitution. So I'll go ahead and write out what my u would be, which is secant of x. And my du is this secant of x tangent of x dx. So this basically turns into the integral of u squared du. Well, that's just power rule for integration, which becomes 1/3 u cubed plus the constant of integration. So when I work this one out, I get 1/3 u to the 3rd plus its constant. And then I still have this minus secant of x over here with its constant. I can combine the constants together. And I finally end up with 1/3 secant to the third of x minus secant of x plus a constant. Now, I know if you've been watching this video for a while that you're probably about brain dead, but bear with me for just a little bit longer. We've got a little bit more to do. If you look on the left navigation menu, you'll see that we've just completed example 10, and we're about to start type 4. So we have one basic part left to do, which is type 4, and then we have case 3. All right, so let's take a look now at what we've got coming down here. What is type 4? Well, we've dealt with the other cases. Now we need to deal with the case where both m and n are odd and both odds greater than 1. Instead of having one of them be 1, the power of 1, this time they're both odd. So in essence, it's very similar to what we did previously. Your strategy is to get the powers to be even again, so you can use the Pythagorean identity substitutions. So you'll break off one tangent and one secant, and that will give you secant tangent dx, which will become your du. Well, if secant tangent is going to be du, then they've all got to go to secant. So you'll have to take your tangents, which would be to an original odd power minus 1, so that it's even. It's definitely an even number. You'll pair them up, and you'll convert them using the Pythagorean identity that converts tangent squared into secant squared minus 1. So you'll convert each of those, and then you'll have powers of secant in some polynomial type expression with the differential of secant of tangent. Okay, so let's take a look at one of these. This would be secant to the 5th tangent to the 3rd of x dx. So again, we've got odd powers, and we know that in order to use the Pythagorean identities, we've got to have even. So we got to pull one off of each of them. So we don't have a lot of choice here. We're going to have secant to the 4th of x and tangent squared of x. And then we can write the secant of x, tangent of x, the one that we pulled off of each one over here to the side. Now this is going to become part of our du. And we need our u then to be secant, right? Because the derivative of secant is secant tangent. Well, the secant to the 4ths are fine. I can leave those. But the tangent squares have got to go. This isn't the derivative of tangent. So I've got to replace that using the Pythagorean identity. So I need to convert this one using the Pythagorean identity. So this is going to give me the integral of secant to the 4th of x times secant squared of x minus 1 times secant x tangent of x. Now you can do the substitution at any point. Some people like to work with the trig functions. I tend to want to substitute them out early, partly because I'm lazy and I don't want to have to keep writing all the trig functions. So the next thing I would substitute would be u is secant of x, and du is going to be secant of x tangent of x dx, which takes care of the one that we pulled off of each one of them. So what does that give me? Well, if I rewrite it then, this just gives me the integral of u to the 4th times u squared minus 1, which is the product of two polynomials, easy enough to multiply out, times du. Well, if I multiply that out, I get u to the 6th. Remember, add the powers, don't give me an 8. That will give me u to the 4th du. And then when I integrate, I get 1/7 u to the 7th minus 1/5 u to the 5th plus the constant of integration. And I can go back to the original, which was u is secant of x. So I get secant to the 7th of x times 1/7 minus 1/5 secant to the 5th of x plus a constant. All right. Hopefully this is starting to sort of seem like, oh, okay, I see that there's all these different cases and subcases, but I don't need to memorize them. I just need to remember I'm trying to build a du, and then I've got to have an even number of the others so that I can convert anything that isn't the antiderivative of this into a Pythagorean identity where it does have the antiderivative of it. And that's our basic strategy. Now we have one more case that we need to cover. That's our last case here, which is that the power on secant is odd and the power on tangent is even. So we have secant to an odd power, tangent to an even power. Now, these are the ones that, I hate to say it, but these are the absolute worst of the worst. These are the hardest ones. Now, we've already seen that secant being raised to odd powers is difficult, integration by parts. And we see again that we have secant to an odd power here. So don't be surprised that we're going to have multiple integration by parts creeping in. The problem is we've got an even number of tangents and we've got secant to an odd power. Now there's more than one way to approach these. You can do it more than one way, all right? And they will work. They may give you solutions that look different, but they'll be equivalent, all right? I'm going to teach you what I consider to be the most straightforward strategy. Like I said, there's more than one way to go, but this is the most straightforward. We're going to take the tangents, since there's an even number of them, and we're going to convert them into powers of secant using the Pythagorean identity. Then that gives me all secants. And then I'm back to that previous part where I was integrating powers of secant only. So that makes it a much easier strategy. And again, there's more than one way to go here, but that's basically what I'm going to try on this particular one. So what we're looking at on this one is we want to integrate tangent squared times secant cubed of x dx. So I'm going to take the tangent squared and I'm going to convert it. So this is going to become secant squared of x minus 1 times secant cubed of x dx, right? Now, how do we handle this from here? What's our next step? Well, the obvious thing to do is the distributive property and break it into two integrals. If we do the distributive property and break it into two integrals, we end up with the integral of secant to the fifth of x dx minus the integral of secant of cubed of x dx. Now, I should be hearing cheering out there, all right, while you're watching this video, because we've already evaluated secant to the fifth of x dx and the integral of secant cubed of x dx. So all you need to do is go back to those previous parts, borrow the solutions that we found there, plug them in, and we'll be done, all right? So this is the most straightforward way of dealing with this subcase, all right? So let me go ahead and see if I can find the solutions to those. I don't know if I copied them or not, but here's basically the solution down at the bottom. Looks like I did not copy them off. But secant to the fifth of x was in part 3. Is that this one? Yes. So secant to the fifth of x was example 8. And that came out to be this expression right here, which you would then add onto secant cubed, which is this one here. So it would be the sum of those two different ones, or difference rather, of those two coming down here. All right, so I will leave it to you to do that one. This does complete our discussion of trig integrals. They are quite difficult. There are many, many different possibilities, but the strategies are very, very similar. Build your du, get even powers of the others so that you can convert them into all the trig function where the derivative of it is the du part, so the antiderivative. All right, so hopefully this makes sense to you. And in the next video, we'll be taking a look at something that's different. It sounds similar, called trig substitution, but it is utterly and completely different. So do not mistake a trig integral with trig substitution. All right, so join me in the next video where we look at trig substitution.